Thank you very much. It's a pleasure to have this opportunity to talk to you about some of the stuff that my lab has been doing over the past couple of years. And of course, a pleasure to be here at this incredible gathering of people interested in AR and things beyond. So I'm going to start by mentioning this general notion of task assistance. I think that many of us believe that this is one of the really important areas for augmented reality, showing people how to do stuff. And here you're seeing some imagery from a project that my lab did a couple of years ago, in which we were trying to build and design maintenance assistance that could be used by people like this young Marine, for example, in the turret of a light armored vehicle performing a task. So how can we use AR to effectively get people to do things that they might not be able to do all that well on their own without documentation, and make better documentation than the kind that is currently delivered via more conventional, more classical media. Now, my lab has been doing stuff in AR with task assistance for many years, coming up right now in 25 years. You're seeing a couple of little still images of some of the work that we've done over that period of time. And what I wanted to do is to move from talking about AR task assistance to talk about the notion of remote task assistance. So it's not just that you are working by yourself, having the system or having the documentation tell you what to do, but rather you are working in collaboration with other people. So to start with non-AR remote task assistance, there's terminology that is commonly used amongst folks who do remote assistance. And there's the idea of a subject matter expert, normally pronounced as SME, and we're going to have a remote SME interacting with a local technician, which we'll abbreviate as tech. And so the idea is here we have someone, the tech, who's probably younger, more willing to travel to places where things need to get fixed. Our SME is a subject matter expert because they've spent probably a lot of time learning and getting to be expert at something that local tech might not be expert at. They may be older, wiser, maybe less willing to travel. And the idea is that there's probably fewer of them, and they want to be able to assist this person who's boots on the ground, basically, off what might be even thousands of miles away, performing some task. Now, historically, of course, when the telephone became available, people used to make phone calls. As smartphones became available, you could make phone calls without having to go to a place where there was a phone. As networking became available, you could do remote network diagnostics. As video became available, you could at first do things that involved hardwired video conferencing. And of course, nowadays, we all take advantage of the fact that we can run any of a variety of software solutions on a smartphone that lets us send video from front and or back-facing cameras to other people who can look at what we're seeing and be able to go and show us what they're seeing. So this notion of being able to have people through a variety of conventional media communicate is something that's become extremely important to people trying to accomplish tasks and get assisted by people helping them remotely. So in addition to just the classical things I just mentioned, there has been over the years, many years, some additions that people add to stuff like this. How many people here are familiar with the word telestrator or telestration? So this is the concept literally dating back from the 1950s, developed by a physicist who is using it to explain things to people, of being able to draw on top of a TV picture. You know, most of you are familiar with this, and drawings on top of pictures of people playing sports, for example. And it's really useful to be able to go and get that drawing on top of a view from a camera. Video mixing, being able to mix video from one camera and another camera, and maybe those cameras are not even in the same place, and now you can get a video composite. So this is something that people have been doing for quite a while, and to just make this a little bit more concrete, I'll show you some stuff that we've been doing back a couple of years ago. You're seeing at the left a view from the standpoint of a technician, and what they're seeing basically on the right is a combination of the view of a subject matter expert. In this case, that's the hands of the SME photographed against a green screen background, We're subtracting everything except for the hands, the non-green stuff, and then it's being overlaid on the left on top of the tech's view. We're assuming the tech has a camera of an engine that they're going to be working on. So show you another example of this. Again, those are the hands of someone who is not in front of an engine, just being superimposed, courtesy of chroma keying, very standard video technology that goes back for many, many decades of being able to show something in context, in this case, video mixing things together. Here's another view, but instead of using an opaque view of the hands, we can make them transparent, so you can see through them. That may or may not be useful depending upon the task. This is all very, very standard kind of stuff. Here's a slight variation on it. Now, instead of the camera being a regular camera, it's a depth camera. So we can combine together things like tracking depth, courtesy of the depth camera, tracking color and being able to use the color to segment, and in this case, that rather blocky looking hand on the right is actually able to be seen in 3D because it's being tracked with a depth camera, as you're seeing over here in my lab with my student, who's using that overhead Microsoft Kinect, looking down at his hand, and the green screen as well, which we can use for different purposes. So, I've talked about non-AR remote task assistance, and good though it can be compared to none, it has problems. The SME and the tech, literally they live in separate environments. They're in separate physical places, they're in separate virtual spaces. They communicate through overlaid 2D media. You can hear their overlay if they're talking to you in audio. You can see their overlay if they're showing you stuff in video, like the overlays that I just shown you. The video, if we want to home in on visual stuff, the view you see is defined by one or more cameras. You literally will see that camera's view. You may need relatively high bandwidth if you're trying to get good quality video across. The video is literally showing you what the camera sees, and that may mean that there's a lot of detail that's potentially confusing, that's unnecessary. Historically, when people make maintenance manuals, back before the age of Photoshop, back when there were not computers involved in making them, people took pictures with cameras, but they didn't just use the pictures, they turned them into illustrations, costing time and effort, line drawing illustrations. Obviously, not drawing the candy wrapper on the floor that wasn't important, leaving out the details. If they used the photographs, they would have airbrushed them, literally using the precursor to Photoshop, in which someone, a very skilled technician, would go in and modify the image to be able to do the things that nowadays people do with Photoshop, often to highlight things, get rid of unneeded details. But when we have live video, we have all those problems. So what I wanted to do is to segue to talking a bit about the idea of doing remote task assistance with AR, of doing it collaboratively, of doing it in a way in which the SME and the tech share an augmented environment. So they're going to work together in some way. So how do we do that? Here's kind of like a little drawing of one particular scenario. This is one that we've been interested in my lab. Here we have on your left our local technician. They're wearing eyewear, as you can see over here. They're looking at their task domain. In this case, it's a little line drawing representation of an aircraft engine. Here's our remote SME. Here I'm showing them actually using a non-head-worn system where the eyewear that they're wearing is literally just stereo glasses, enabling them to look at stereo monitors. The point is, there's lots of different ways in which we can implement these environments, lots of different technologies. I'll talk a little bit about them in a couple of minutes. But the idea is we've got our remote SME, our local technician, and one of the things that we're very interested in is, given that we've got this remote person who has spent years learning how to do something well, they're a bit older right now, they maybe don't want to go and travel a lot, there may be someone who might be thinking about retiring. Can we make an environment in which that remote SME is going to feel as happy as possible about what they're doing, is going to have the minimal amount of friction to accomplish their task, because there's fewer of them than the people who are actually out there in the field? Can we maybe even allow them not just to spend one-on-one time, literally one-on-one and with no one else, But instead, I think of this as being a bit more like the notion of the chess grandmaster who's playing with a novice. And generally, if that happens, you're not going to have the grandmaster playing one single person. They may be doing these exhibitions where they go round robin, maybe they're even blindfolded. There's a bunch of people. They move from one person to another. And meanwhile, people have a chance to ponder their moves while the grandmaster moves on to somebody else. And so, can we have our remote SME in that way be able to perhaps work with a whole bunch of people moving from one person to another because they don't have to physically change their environment. They can literally just work from one place and be able to advise a bunch of people remotely. So, lots of questions that we need to ask and answer. I'm just going to sketch some of the different questions and then go into looking at some of the things that we've done that pose specific answers to those questions, just to get a sense of some of the sorts of things that people work on in this domain. So, asking about our SME, asking about our tech, are they working in the real world? Definitely so in the case of the tech. Are they working in a virtual world? Well, maybe they're going to have virtual stuff added to their real world, but if they're really trying to accomplish a real task, they need to be very present in that physical environment, potentially even a very dangerous one. But can the SME perhaps not have a matching physical world? Maybe they can have a virtual representation of that physical world and be able to do virtual things that mean something, that get reflected to, get transmitted to the local tech, that tell them, explain to them how to do stuff, be able to get information from the tech's side that let the SME understand what the tech is experiencing and then be able to help them. Do they work at full scale? Well, if you're actually performing a task hands-on, you probably are, like the tech, but maybe they work at a different scale. And I'll show you some examples shortly in which our SME is working and on a scale model. So instead of having a full-size version of something, they can be working essentially in miniature to be able to more quickly move around because they're moving around virtually. Do you see your own view from your own eyes or from cameras mounted where your eyes are, or do you see somebody else's view? If you're the SME trying to understand what the tech sees, maybe you literally want to see through their eyes, see through stereo cameras that the tech is wearing. Maybe you want to see from a completely different vantage point because there's other cameras in the environment. Maybe you want to see your own personal view of a modeled version of the tech's environment where you completely control things with your head position and orientation. And I'll give you examples of some of those shortly. If I'm seeing somebody else's view, am I seeing it live? That can be very nice, but maybe sometimes because that other person is moving around a lot, I don't want to literally see what they're seeing as they move their head around like this. That maybe is going to be uncomfortable. Maybe there's something I want to look at and I don't want to be beholden to where their head is positioned and oriented. So maybe I can freeze their view and be able to see through their eyes, but at a specific point in time frozen. More stuff. We're talking AR, so that means displays of some sort. Is the display going to be worn on the head? Is it going to be held in the hand? Is it going to be stationary in the environment? Is there more than one? Maybe there's a combination of ones that are held, worn, and stationary. Is the technology optical see-through, in which we're seeing directly to the world, like the Meta eyewear that you were trying in the back? Photons from the world really are going to land on your eyes and then be overlaid, augmented, mixed with virtual stuff? Or is it video see-through, where you're looking at the world through one or more cameras? The cameras may be ones that you wear, and again, they may be cameras that someone or something else wears, and you're able to go and see the camera eye's view of the environment, again, mixed with virtual stuff. Is it projected? Maybe you're not even wearing any display at all. You're looking at an environment in which projectors that you wear or that you carry or that are mounted in the environment project additional information on the environment itself, highlighting stuff, labeling stuff, showing you things that are reflected from the real world. How do we track stuff? If we want to be able to go and overlay things, it's very important for us to know, or for the system rather, to know where our head is, how it's positioned, how it's oriented. Are we wearing a tracker? Are there trackers mounted in the environment? Are there things mounted in the environment that communicate in some way with what we're wearing as well? There's lots and lots of different technologies for tracking both people's heads and as well stuff in the environment. And I'll show you some examples shortly when I talk about some of the things that we've done in particular. And you know, it's not just where it is, it's the technology. Does it use computer vision? Does it do it with one camera? Does it do it with a constellation of many cameras? Are they monochrome cameras, RGB cameras, nowadays RGBD cameras in which they can tell in a variety of different mechanisms the depth at every single one of the pixels? Are we using electromagnetic trackers, as was historically done many, many decades ago in some of the earliest VR systems, and now we're seeing come back at much lower prices, at much better quality, in things that are designed to be sold to consumers, gamers in particular. Is there an IMU or IMUs, inertial measurement units, that are measuring essentially acceleration, that are measuring with gyros and with accelerometers, and usually included in IMU, though it's not really the case, measuring the Earth's magnetic field literally with compasses. Are we using some kind of satellite navigation? GPS is one example, of US constellation example, of global navigation satellite systems, the politically correct generic term to refer to GPS and GLONASS and a variety of other constellations, more or less functional, that enable people with receivers to be able to figure out where they are literally anywhere on Earth that gets to see the satellites. So there's lots and lots of different approaches that, depending upon whether you're indoors, outdoors, how much you want to spend, how big you want the thing to be, how accurate you need it to be, different approaches for doing the things that I just mentioned. So I'm going to talk about two tasks in particular, okay? One of them is the idea of getting a technician to move to a particular location, because there's many tasks in which you have to be somewhere. And the other one is getting the technician to then perform the correct task when they're at the desired location. So first, getting the tech in place, okay? Now, why? Well, the tech may need to observe something. They need to understand their environment. They need to be able to figure out if something's wrong. And if the tech is bearing sensors, for example, like cameras, this also may make it possible for the SME to be able to observe through the tech's eyes and then be able to give advice about what it is that they're seeing. Now, once you figure out what's going on, the tech is there because they can actually physically do stuff, and so the tech can act, and it also means that the SME can communicate with the tech, can demonstrate to them something that they need to do, can put stuff in their environment that helps them act in an appropriate fashion. So how do we do this? Well, we can do things like pointing and gesturing in the current view. So you can, assuming that we actually have the ability to see something that's worth pointing at, you can have a remote person pointing. And in fact, you know, this again goes back to literally the 50s, in which you have the ability to draw on top of the video view and then display it to people. Lots and lots of different ways of going and doing this. I can show you a different view. I can say, instead of looking over here or looking over there, gesturing in what your camera shows you, you know, why don't you go and see what I'm going to show you right now? In which case, of course, that gets a little messy if you don't know how to get to that different view from where you are at the moment. Now, one thing that AR and VR let you do, because we're now talking about being conscious of and having the system know about a 3D world, that means we can annotate the environment in 3D. We can point in 3D. We can leave stuff. We can create physical or virtual annotations in that 3D environment that are designed to assist you in figuring out where to go. So let me give you now an example of some of the work that we've done on trying to do this. And we'll talk now about just this idea of getting the tech to be in the right place to accomplish a task. And so thinking about some of the different approaches that I mentioned before, what I'm going to show you, I'm going to show you a couple of stills first, and then I'm going to show you a little video, is we're now seeing from the eyes of a remote SME who's looking through a video see-through display. So they're wearing eyewear that has cameras built into it. They are looking at a little Lazy Susan that's in front of them, and then that Lazy Susan is tracked by a overhead tracking infrastructure, a constellation of cameras. It's looking at some known artifacts, little retroreflective spheres in known configurations. And mounted on that little turntable is a scaled-down version of a Rolls-Royce Dart 51 aircraft engine. So this is a big aircraft engine, or actually not all that big an aircraft engine, but it's bigger than a little turntable. Dart 510. And that's been scaled down to being something around maybe yay big or so. And that's going to enable our SME to be able to do something they couldn't easily do in real life. Instead of having to walk around the engine, getting up out of their chair, or spin the engine around in front of them, which is really not going to happen, they're able to simply easily spin that turntable, and they're going to point to a place they want to have the tech to go. And what you're seeing here is doing some hand tracking, in this case using what was called NimbleVR before it got bought up by the Oculus folks. They're having their hand tracked by overhead depth camera, and they're pointing at these little iconic representations of viewpoints that are possible ones for this particular task that they would like to have their tech go to, okay? And then, what is the tech going to see? How does the tech get to go to one of those places? The tech is going to see in their environment, and the tech really is walking around because they really are in front of that engine. And here you're seeing one eye of a video see-through display overlaid on top of which, of this view of part of the engine, is this thing that essentially looks like a kind of splayed picture frame window. And it basically is going to be the representation of where the SME wants the tech to go. So let me show you what that looks like over here. So here we have our SME. They're spinning their little turntable. This is what they see through their video see-through display, that little scale-down view of a model of the turboprop engine. Representations of the different places they can get the tech to go to. They're going to pick one. And here comes our tech. He's wearing a tracked, head-worn video see-through display, a Canon HMA1. And now, this is what he sees through one of his eyes. And there's our representation of that picture frame window. He's going to get his head inside of it. He's going to look through. Here we have the pointing hand of the SME pointing to something that he wants him to look at. So that's one way of getting our tech in place. Now, let me show you another approach. Here's another way. The one I just showed you is designed basically to have a lot of slop. We actually told the tech, you need to look through that window. So what does that mean? Some people, you tell them to look through a window, and if the window's over here, they're going to walk right up to it and they're going to stick their head through it. There's other people, the window's over there, they're standing back over here, they're looking through the window, right? You know, different people interpret that differently. So here's an approach to try to get people to be much more precise about stuff. So you're seeing a little kind of doll head over here. It's basically, it's a mask, and it's essentially around human size. And the idea is when the tech sees the mask, they're supposed to stick their head into the mask. So I'm going to show you a couple of stills and show you a little video. And one point I want to make is what I just showed you before, you were seeing things life-size. That tech was actually walking around in a tracked environment. I'm going to show you basically something that's not life-size. The stills I'm going to show you and the video are all done basically with a scaled world. We're doing marker tracking, head-worn display with a camera built into it. It's looking at a little rectangular parallelepiped, basically kind of like an elongated rectangular prism. It's got some markers on the side that are being tracked using a software-based, camera-based marker tracking technology. And that basically is what controls the position and orientation of the engine. And what you're going to see literally is someone picking that up and putting their head into the mask like that. So that's much, much cheaper to do. You don't need an entire tracked room. someone who's trying to mock things up and see, get at least a beginning of an experience of what it's going to feel like, can do this very, very quickly. So this is basically kind of like an implementation strategy that we often do in AR. Rather than building the big full-size thing, we build a little miniature version of it first, makes it much easier and faster to experiment. And so here's that little head that I was showing you, slightly different viewpoint. That, instead of being the real engine, is the scale model. In the distance for scale purposes, that's a keyboard, okay? So that's our regular normal-sized computer keyboard. We're moving our head in closer and closer. There's the inside of the mask. We get closer and closer. In this particular technique, the mask is going to start fading out as you get closer and closer to it. We're nearly there right now and getting our head inside of it. And so this is a little video that shows what's happening. So here that's on the little turntable spinning around. We're moving our head closer and closer, putting it into the little mask over there, and then you're seeing through the eyes of the mask, okay? So I showed you two different approaches over here, okay? And so, oops. So we have two different approaches. One of them was this picture window that I'm showing you on the right. And I mentioned the slop that you have, is sort of unclear exactly what you have to do. And the other one is that mask. Now that mask is really precise. If that were really a physical mask that you could actually feel, and it was the right size for your head, you'd be able to get into it really, really easily, because you just put your head up against it, and it stops your head at the right places. And if it's a custom-made mask, it'll fit literally, well, like a glove is probably the wrong analogy, like a mask, okay, like a custom-made mask. Now the problem is that this is not really a physical mask. I don't know anyone who's done the right kind of haptics to really make something that looks like a mask and really feels like a mask. And it is a very precise way of specifying something. And in graphics, we often talk about a Parafrustum, basically a truncated pyramid. And here we're looking through it. And basically, it's defined in part by a look from point to a look at point. It defines a very precise vector that essentially controls in part some of the degrees of freedom of orientation and position of this little truncated pyramid. That's really precise. So we now have this little contradiction going on. This precision, which is really hard to get someone to do exactly. This sloppiness, which is easy to get someone to do, but what are they going to do? It's really hard to tell. Different people treat it differently. And we had observed in the work that we're doing that there's many tasks in which I don't want to get you to be at an exact position, looking at an exact orientation. That's overkill, okay? When I'm giving this talk right now, I can stand over here, I can stand off on the side, I can stand back like these. These are all perfectly reasonable things for me to do. I can look this way, I can look that way. This is probably a weird thing for me to do for most of the talk. With my back to you is weird to do for most of the talk, right? So there's some things that work, some things that don't. It's just much fuzzier than being in a very precise place, looking at a very precise orientation. And so what we tried to do is to come up with a way of essentially combining these two things in one approach. And it's something we call a Parafrustum. And you're seeing a sort of third-person view of what this looks like. That big thing over there, which looks kind of like an airbag in process of being deployed, is part of a visualization that's designed to be parameterizable so we can get you going from a very precise position to a much broader range of positions, a very precise orientation to a much broader range of orientations. And the idea here basically is that normally we talk about this truncated pyramid. That's how we talk about the camera model in computer graphics in general, and as well VR and AR in specific. And so as I said, there's a look from point and a look at point. And what we did in this work is we generalized this. So we still have that truncated pyramid, because that's to be represented by one of the eyes of our display. But we're now going to have a look from volume and a look at volume. And so to get back to this picture over here, you're looking at a head volume and a tail volume. And the way this works is the head volume, which in this visualization you're going to see in your environment. And so my student over there, if we want him to get into what this defines as a legal position, he's going to have to get his head inside that head volume. And it turns out he sees this staring there in front of him, and it's going to be very easy for him to ballistically insert his head into it. And when he's inside, I'll show you what we do in our visualization to be able to go and figure out that we're actually there. And then when he's inside, there's a tail volume. And let me explain how that works. The way it works basically is you got to get your head fully inside the head volume, and then the tail volume needs to be cut by neither or both of the left and right sides of the view volume. So that little tail volume, in this case, it could also be very big. It has to be either entirely inside of our view, or it has to be sufficiently large that it's off to the left and off to the right. So it's off only to the left. Well, look a little bit more towards the left until it gets inside, or until it gets out on both sides. Basically, it's kind of like a heuristic for seeing as much of it as possible. Same thing for above and below. If it's fully inside, that's okay. If it's completely encompassing it, really, really big, that's okay. If it's above a little bit, then you need to look up a little until we verify that it literally is going to stick out above on the top and the bottom, okay? And if we have stereo, which we do, then instead of comparing the tail volume with one of those frusta, one of those frustums, then we compare it with the intersection of the left eye's frustum and the right eye's frustum. So just to make it clear, I'm going to show you a couple of stills, and I'm going to show you a little video of what it looks like from one eye of someone wearing the system. At the upper left, you're seeing a particular representation of a parafrustum, a not all that big head volume that you have to get your head inside of. This would correspond to a task in which there's fairly tight constraints about where the eyes need to be. In the middle one at the top, we're getting closer and closer to this ovoid-looking thing. In the upper right-hand corner, we're now inside. You're seeing some ribs around the outside. When your head's properly inside, when you can see the full tail volume, which has a thin red outline over there, then those ribs go away and everything's okay. If you stick your head all the way through that head volume, which you're not supposed to do, but you could do, then that tail volume gets to start glowing this angry-looking red. If you just persist and go further, it gets redder and redder. If you go cut it by only one of the top and bottom, or one of the left and right, you'll see some white highlights around the side. And if you then basically play by the rules and pull your head back inside, then you're seeing only this thin outline around stuff. So let me show you what this looks like. This is one eye, video see-through, person wearing this Canon HMA-A1 with the video being recorded from one eye. And so there's a representation of one. They're going to stick their head inside. When they're inside, the yellow goes away, and we're inside. The ribs go away. We're cool. But this person just goes further forward. They're not supposed to. It gets big and angry red. And then for the sake of a video, they're going to show you that, it's not good to get a cut on the sides over there. And then if they back their head back inside, then they're okay. And this one, now as we're moving around, you're seeing the permissible slop for this particular task, and then they're pulling their head out over there. So we've actually done user studies comparing this with a couple of other approaches to be able to see what kinds of things can get done. And we're able to show that with these looser constraints rather than tighter ones, people take less time to be able to assume a reasonable pose. So now I want to move to talking about actually performing the task. So once you get somewhere, how do you do it? I'm showing you a bunch of different views of different approaches that we've taken. I'll talk a little bit about these in a second. And they're showing basically people interacting from the standpoint of the tech and standpoint of the SME. And let me try to make this a little simpler. So there's lots of questions. I'll show you a couple of particular solutions in stills and then in video. One of them is, how do you represent the SME or the tech in the other person's view? And so one thing you're seeing on the left is we're representing the head of one of the people in the other person's view. We're not showing you something that really looks like someone's head with their 5 o'clock shadow and a little bandage when they cut themselves and their hair looking exactly the way it looks. We don't need any of that. We're seeing this very simple, rigid representation of the head, which works surprisingly well for letting you know what they're looking at, with the assumption that they're looking relatively straight ahead. We're seeing representations of hands in this case, tracked using this off-the-shelf hand tracking technology. Now on the right, a couple of other approaches. We've used hand tracking. We've used tracking of objects like the Wii remote control that people might recognize in the middle picture. That's as seen from the SME's eye view. We've annotated it with information what the buttons mean, so as the button meanings change, you don't have to remember stuff. On the right, you're seeing just a plain arrow. So this is tracking a remote control being held by the SME, but the tech, rather than needing to see that remote control with its buttons, they can't push the buttons. Why should they see that? All they're seeing is this very simple pointing arrow. How does the SME interact? I showed you using that remote control. Here's a couple of other things. Here we have a tracked mouse with those little antenna coming out or part of a optical tracking infrastructure.
Sorry to interrupt, but we're 7 minutes over, and I didn't
No,
know if you
we're
wanted time.
not. I have until 1600, till 4 o'clock.
Oh, there's supposed to be a 15-minute break.
No,
But-
it's 4 to
but,
4:15, so I
you-
have until 4 o'clock. That is
Don't
what the
forget
schedule
about questions,
said.
though.
Okay?
Questions.
Okay, so we're seeing different representations of that. How do we represent what's going on over here? Can we do it in AR? We can do it in VR. And so in AR, you're going to be sending, in this case, remote AR, you're sending video from the remote, from the local tech to the remote SME, along with 6DOF information about objects that are being tracked. And in VR, because you're not sending video, much less bandwidth, much more like what you'd be doing with a multiplayer game with people at different locations, sending just 6DOF poses of stuff. And also lots of different interaction techniques for how we do things. So the last thing I'm going to do, I was trying to leave 5 minutes for questions, is show you a little video of what some of this looks like. Here we have our tech. The inset shows the SME. The SME is seeing things in VR. The tech is seeing things in AR. I'll pause this for a couple of seconds. Side-by-side stereo that you're seeing on the monitor over there being sent as correct stereo to the SME. And our tech, basically, you see in 2 monitors over here, the left and right eye views of what it is that you're seeing. We'll see them up close and personal-like in a few minutes. And they're being instructed to perform a task by the SME, who's also talking with them. We're assuming that we have video. Here we're looking at a somewhat more complicated task involving more arbitrary 6 degree of freedom position and orientation being communicated to the tech by the SME. Okay, so this is a tech's eye view. This is a task in which they're being shown where to position something. There's some little lines that are connecting stuff. Here's our SME's eye view with an inset of the tech. The SME's seeing things in VR, the tech in AR. And what the SME is doing is, because they can't really pick up a real thing, they are working with these representations, virtual representations of what the tech actually has in their environment. So in this case, they are picking up a copy, a replica of one of these representations, picking it up, moving it around, and here, literally just by grasping and ungrasping, when that little cube turns red, it means that they're clutching, they're grabbing hold of something. They can pick up this virtual representation, and they're going to be able to go and show the tech where they want it to go. So let me go past a couple of techniques. Here's one technique we have where our SME is pointing at a position on the top, making a copy, a replica of that bottom piece. They can position and orient them as they see fit. And they're going to draw lines basically connecting places on the top to places on the bottom. This is one way of being able to show the tech how they would like them to do stuff. And now you're seeing the tech basically completing the task, picking up the real top and putting it on the bottom. Here's another approach where our SME picks up a virtual copy and demonstrates what they want to have happen. So whenever that cube goes red, they're demonstrating. And now one issue here is because the SME is working entirely virtually, they can do stuff like this, which of course can't happen, right? And that can produce results like this that are just wrong. I mean, that thing shouldn't be going through the bottom. So an approach we take to do this is we allow the SME to set constraints saying that what things can and can't happen. So here, when the SME is now having specified some constraints, putting the top on the virtual bottom, if they get close enough, the system automatically aligns and snaps things into place. So they can very, very quickly show something without having to do this task that would normally have haptic feedback without the haptic feedback. And here we're seeing the tech's eye view. They're grabbing hold of the real top, and they're about to put it in that location where you can see the virtual representation of what the SME actually inserted over there. So in the interest of time, I'm going to stop short right now I'm going to go actually past this other work that we've done, acknowledge the many folks who participated in this work. Hopefully have a little bit of time left for questions right now. Thank you.
Thank you, Steve.
Yes.
Hi. Was there, after you had trained somebody initially,
Yes.
and then, how long was the next level? Were they able to get it faster? How many
okay.
training sessions, all that?
Okay, so the study that we did were single session experiments, and we basically worked with dyads, people who came in together, and based on doing some spatial ability tests, we assigned people to be either a SME or a tech. And because this is a kind of complicated system, to sort of hedge our bets, in addition to having people who were literally trained during this single session to be a SME, that's the one that's hard. We also had kind of a ringer who was one of the experimenters, one of the researchers, who also, in process of training our novice SME, who is coming in as part of a recruited subject pool. They also worked with the recruited tech, but now because they've done this a lot, we're able to get data both on novices doing stuff and as well also on someone who, although they don't do this for a living, did it enough and knows how the technology works to be able to work really well. So to make a long story short, we were able to show that of the different techniques, that one of the techniques, the one that involved the demonstration, actually worked a lot better than the other ones did. But one thing I'm looking forward to doing is I'm about to get funding from part of the Navy, which is very interested in this maintenance and repair task. And there we're actually going to be working with people who really are doing this stuff for a living, for whom this really matters that they do it right, and be able to go and train them in more than just the single session kind of experiments that we're doing right now. So I will hopefully by next year be able to go and answer some of those questions. Yes.
So many of the techniques you've shown require an extensive amount of 3D content, not only the virtual models of the thing you're repairing, but for example the Parafrustum technique and also the thing of the jet engine, where you specified which viewpoints are allowed.
Yes.
So for example, for the Parafrustum, how do you envision the authoring of that?
Very good question. So I see two basic ways to do the authoring, okay? One of them is basically one in which a person who knows about the task essentially demonstrates and says, this is a good place to be, this is a good place to be. Kind of like the demonstration I did before, right? And then as they're demonstrating, the system is essentially extrapolating and coming up with a proposed visualization, and then you could say, no, that's too big, maybe I'm moving a little bit tighter, I didn't really mean to be over there. Oh, not just there, maybe there as well. Okay, that's one approach. Another one is more theoretical and analytic, and that's if we have a really good model of the task and what needs to get done, and of the geometry of the parts, which as more and more as things get done with CAD we will have, then we can basically analytically come up with the positions and orientations that will be good for performing a task. So I think one or the other or a combination of both will be a very nice way to do this depending upon the particular domain. Welcome. Yes?
Are you doing any work?
I think we need a mic over there maybe, because I don't think anyone else can hear you.
Are you
Yes.
doing any work with 3D point clouds where you have a laser scanner that would on the fly, let's say there's a situation that's unexpected.
Yes.
You don't have the chance to have taught the system beforehand how to operate, but you need the SME to be able to understand the current situation.
Yes.
To very rapidly laser scan it with a hand laser scanner and generate the point cloud.
Okay, so two answers to that. One is it turns out that the techniques that we have, the demonstrational one, although I didn't tell you enough about it to make it make sense, I showed you the SME working entirely in VR, but we also can let the SME work in AR, and it turns out when you're getting that camera view from another person, that there's actually a number of things you can do without any need to appeal to any kind of scanning other than literally looking with a remote pair of cameras. So there's a lot of interesting things that you can actually do. I'm happy to talk about them with you afterwards. However, yes, because RGBD cameras are incredibly inexpensive. We have plenty of them in my lab. We do stuff using them that's not really the research that we do. So we've used Kinect Fusion, for example, which is a Microsoft product, to be able to go and take Kinects and use them to build up models of stuff in the environment. As those cameras get better and better, the models we're going to be able to build are going to get better and better and better. And the idea of having someone wearing these sensors walk around an environment, doing what often gets called SLAM, simultaneous localization modeling, building up a model of the environment while they know where they are relative to that, is an extremely important one. Lots of research is being done by people getting lots of funding to do it better and better and better. Every passing, literally week to month, you're seeing progress in that domain. In a variety of conferences in which people who do that stuff talk about it. So that's very exciting. That low-level technology is not something my lab works on, but it is something that we're interested in using. It's just, in general, hard, right? It is not easy to do that, let alone in really uncontrolled environments, including outside during a stormy day when the rain's coming down. That's really, really hard to do.
That's about all the time we have questions for.
Thank you.
Steve Feiner, Columbia
Stick
University.
around to talk with folks.